Okay, so let's continue on looking at the two-body problem. This is where we are so far. We got Pluto. We found out the distance from Pluto, this RCM here, little RCM, is the mass of Charon divided by the total system mass times this distance between Pluto and Charon. So that's how far Pluto is from the center of mass. So now we want to figure out what these two guys do, and we're assuming they've got some kind of circular orbit. And so what will happen is, you'll recall for a closed system, the momentum is conserved, so P total is constant, and you remember velocity of the center of mass is P total over total mass, right? Or really just capital M here, but it doesn't matter because the point of this equation is that if this is constant, if there's no outside forces pulling more strongly on one than the other, and there aren't. I mean, so as I said again, the sun is pulling on both of these, but it's giving them the same acceleration. So we can sort of ignore the sun for now in that sense and just say, eventually this whole system is going to circle the sun, but for now we can just treat it like it's a closed system dealing just with its own parts. So we can say it's got a constant total momentum, which means the velocity of the center of mass is going to be constant. So this is just going to keep moving basically in a straight line, or it's going to curve eventually around the sun. And these two things are actually going to orbit it. So this does not accelerate. The center of mass position does not accelerate. What happens is that both bodies are attracted to each other and move in circular orbits around the center of mass. And Pluto-Charon system is somewhat unique in that it's one of the only, well, it's really the largest system in the solar system, the largest pair of objects in the solar system that you can really observe this very well for. Earth and the Moon do it, but in that case, the center of mass is inside the Earth, so it just appears as this sort of wobble in the Earth's movement. But what really happen, it's really dramatic with Pluto and Charon. So they're both going to orbit the center of mass, and they're both always going to be opposite each other, because they have to be for the center of mass to still be there. So when Pluto is moved to here, then Charon is going to be up here. And there's a wonderful, if you go and Google center of mass on Wikipedia, so I'm just going to write it down, Wikipedia, and you look for center of mass, and you go most of the way down the page, there's this really nice little animation somebody's made of different systems with different sizes of bodies orbiting the center of mass. And so there's one that's like Pluto and Charon. There's one where it's two objects of the same mass. There's one where one object is way bigger than the other. It's neat, and it sort of gives you a good intuitive feel for how these things work. So then when Charon is here, for example, Pluto's going to be down there, and so they're going to take some period of time to orbit each other, and it's going to be the same period of time. And I've just written over my orange equation, but hopefully you can remember what that was. So we have really now actually all we need to solve this. So to keep Pluto going in a circle, it must be accelerating, right? So this is Pluto's acceleration. I'm going to call it AP, which means there must be a force acting on Pluto, some force from Pluto causing it to accelerate. What's that force? Well, it's gravity, and it's got to be gravity. What's exerting the force on Pluto? Some people will say the center of mass is exerting that force, but the center of mass is not actually an object. There's nothing there. You could take a spaceship out to the center of mass and you'd find just space. There's nothing there. What's exerting this force on Pluto is Charon. So it's the gravitational force between Pluto and Charon. So we take, we want to find the magnitude of this force. We take our gravity equation, just the magnitude version, so there's no, this is all scalar, there's no vectors in here because we know the direction of it, right? So we don't need to worry about that. So it's capital G times the mass of Pluto and the mass of Charon divided by, and then the bottom, remember, is the square of the distance between them. So again, this is where people think, oh, this RCM, but no, it's the distance between Pluto and Charon, so it's big R squared. This is just our gravitation equation plugging in Charon, Pluto, and this big distance, capital R, between them. And that, this is the force acting on Pluto, and that is going to equal Newton's second law, F equals ma. So it's the mass of Pluto times Pluto's acceleration. Now, what can we do, knowing that? And so knowing that, we can get it down to, Pluto's acceleration, because we cancel out the MPs, right? MP, MP. So Pluto's acceleration is going to be capital G, massive Karen, divided by capital R squared. Easy enough. Now, what we wanted to find here, and I didn't really say at the beginning what we're trying to find, but we're just sort of looking at this system. Let's find the period that it takes for, so find the period of revolution. Wow, that's an ugly F, of revolution. And so that's the time it takes for Pluto to orbit this once, also the time it takes for Karen to orbit, right? Doesn't that make sense? Because if they always have to be opposite each other, they must take the same amount of time to swing around once. So what we can do here is we found acceleration here, and what we always do with these uniform circular motion things is we find the acceleration twice, once from like a force dynamics and then once from the kinematics of circular motion, and set them equal. So the acceleration, Pluto's acceleration here, has to be equal to Pluto's velocity squared divided by the radius of its circular motion. What's that radius of its circular motion? It's actually this little RCM here, right? Because it's circling the center of mass. It's not circling Karen. It's not this big R. It's this little RCM. So that's what's tricky. For gravity, the distance between the actual objects is what matters. For the circular motion, it's just the distance to whatever you're circling. So v squared over RCM, and we can use a little fact, and you guys have seen this probably 5 million times. Velocity as it goes around the circle is 2 pi times the radius of the circle divided by the period. Sorry, not divided by, it's not squared, just divided by the period. So we can plug this in here, and what we get is 4 pi squared, and then we get RCM, and this is squared, but I'm leaving that off for a moment. And it goes over t squared. So there's our v squared if this was squared, but then we're dividing by RCM also. So that's the extra RCM down here is going to cancel one of these. That's why we leave the square out. So at this point, this is the acceleration of Pluto we got here. This is the acceleration of Pluto we got here, and these are equal. Okay, so this is the acceleration of Pluto due to Karen's gravity, and this is the acceleration Pluto needs to have to go around this RCM circle. So we can just set these two things equal and say this equals 4 pi squared RCM over t squared. Okay, now what can we do with this equation here? Well, let's go back and look. I'm going to switch to blue here. Look at this here. We found what the radius or the distance between Pluto and the center of mass is, which is the radius of Pluto's orbit around the center of mass. We found that in terms of big R and MC and total mass of the system. So we can actually plug that in here, right? Plug it right in for that. And what we get then, so I'm going to copy it on the left-hand side of the equation, is G MC over big R squared. Let me shift our thing down a little. Let's see if I can do that. Whoops. Actually, that's probably not the correct way to do it. Let's see. Bring it back up. And then let's just scroll down. There we go. That's better. Okay. So this is this left side here. And that's going to equal 4 pi squared. And then, well, I scrolled it off. So let me get this back. So RCM is going to be replaced by MC over big M times R. So let me just go ahead and do MC times big R over big M times t squared. Okay, now we can scroll down a little. So let's switch to another color. I don't know, I'm running out of colors here. Let's do purple. Haven't done that. Okay, so we can cancel out the MC, right? And what we get then is, and let's, I'm going to put this in terms of t squared. So I'm going to bring the t squareds up on top here. I'm going to take this r squared and bring this r down to join its buddies here. So that gives us t squared over r cubed equals, and then let's see, what do we have left? So we've taken care of this and this and this. So what's left is 4 pi squared over, bring the g down, gm. And there we go. This is actually, again, we've derived Kepler's. Was that second law or third law? I think that's his third law. I forget. Kepler had 3 laws, and it's the second or the third. Anyway, what's notable about this is first of all that the period of the entire system does not depend on how the mass is broken up between the two bodies. So what you need to know is this capital M is the total mass of the system. You need to know that. You need to know the distance between the two masses. And you need to know, g, which is a universal constant. And of course you need to know pi, and you need to know 4. But if you know all those things, then you can find the period. So it's interesting to point out here that you could take Pluto and Charon, and what I said in class, and this applies, is here's Pluto's really big and Charon's really small, and they orbit each other. Well, they orbit the center mass with some period. But if you took them and smashed them together, and so this distance here is r, right? So if you took them and smashed them together, and then rolled them together to mix them up good, and then you separated them into 2 equal-sized masses, then separate them a distance r again, and give them a little flick to send them into circular orbits around each other, the period would be the same. Because you still got the same total mass in the system, right? And g and 4 and pi squared are all the same. And you've kept the radius the same, or sorry, not the radius, but the distance between them, range, I guess you call it, whatever. Then t squared has to be the same too. So it's interesting to see that it doesn't depend on how the mass is split up between the two objects. It just all it depends on is the total mass of the system. So there you go. That's your basic solution to the two-body problem, where you're just dealing with circular motion. Circular orbits only. You can do it for elliptical orbits. That requires calculus. It gets a little hairier, and I don't want to do that myself, at least not right now. But this is how it works for circular orbits. Very nice. It doesn't work for 3 bodies. 3 bodies. When you get up to 3 bodies, there's a whole lot of simplifying stuff we did here to make this easier. A whole lot of things we knew were always true. Like we always knew we could draw a line from Pluto to Charon, and the center mass would be on that line in the same spot. But when you get to 3 bodies, you don't know that, and you don't have any of this neat stuff that always stays the same. And so 3 bodies gets to be just a nightmare. It is not solvable. It is officially not solvable. You can't actually solve it in what's called a closed form, where you come up with an equation that tells how these things behave for all time. You can do that with the 2-body, but you can't do it with 3-body. So, I mean, if you feel like trying, go ahead, and maybe you'll be the one to discover the solution and get a free trip to Oslo to pick up your Nobel Prize. But I would not make the plane reservation yet. Let me put it that way. So there you go. There's your 2-body problem.